Okay, so we made it through alkanes and alkenes. Now we have to go through alcohols. Okay, alkenes is the most, just letting you guys know. So alcohols, we know they contain that hydroxyl functional group. This is polar and increases the solubility of the alcohol as opposed to an alkane or an alkene. And what does it undergo? Alcohols can undergo combustion, oxidation, or esterification. And we did talk about esterification last year as well when we were talking about condensation polymerization in HL. My gosh, this is already 30 minutes long. This video is so long. I'm sorry, guys. I need more coffee. I might have to take a coffee break. Okay. The combustion of alcohol should be very familiar because we talked about that as well in our thermochemistry unit. But alcohols can, again, like hydrocarbons. Alcohols like hydrocarbons can react with oxygen to form carbon dioxide and water. So this would be the example of the combustion of methanol reacting with oxygen to form the carbon dioxide and the water. And as the homologous series gets bigger, more energy is released because more carbon dioxide is produced. You can see that the difference between methanol and pentanol here, there is only a 1-to-1 ratio of alcohol to the CO2 formed, but as you get longer in the homologous series, like a longer alcohol chain, you can see that now there's a 1-to-5 ratio of the alcohol to the CO2 produced. So that results in an increase in the enthalpy of combustion. You can see the difference of negative 726 here for the smaller alcohol versus the negative 3,390 negative 3,330.9 kilojoules per mole for the pentanol. And just like with hydrocarbons, if there is limited oxygen available, it will form carbon monoxide instead of carbon dioxide. So combustion is the complete oxidation of the entire alcohol molecule. And what do I mean by oxidation? Who remembers Leo the lion says grr. So loss of electrons is oxidation because the alcohol it forms the carbon dioxide, which is the more oxidized form of compared to the alcohol. So combustion is complete oxidation. But it is possible to react alcohols with acidified oxidizing agents, which selectively oxidize the carbon atom attached to the alcohol group, which leaves the carbon skeleton intact. So instead of completely breaking it like it does in complete combustion, and so you have the alcohol and then it forms carbon dioxide, instead of completely breaking it, it actually only oxidizes that OH, the carbon attached to the OH group to form a double bonded oxygen there, but leaves the rest of the chain intact. Don't worry, I will go over the mechanism with you guys. And the most commonly used oxidizing agent to allow this to happen is acidified potassium dichromate. So this chromate 6, right? The V1 represents 6 because that means the chromium has an oxidation state of 6. It's bright orange, but whenever it's used as the oxidizing agent and gets reduced, it is reduced to chromium 3. So it changes to green as it is reduced. So you can actually start out with an orange color and you know the reaction takes place when it turns to green. Yeah. So in a reaction, if you see like an O in brackets above the reaction arrow, that represents the oxidizing agent. So like if you're going to use potassium dichromate as your oxidizing agent, you'd have like in brackets the CR6 to show that that is your oxidizing agent. Okay, so how does this happen? Well, primary alcohols are oxidized in a two-step process. So we're starting here with our primary alcohol because this carbon is only attached to one other carbon, so it's a primary alcohol. We have our oxidizing agent here and heat. So when that happens, we're going to break this oxygen-hydrogen bond here, and it's going to then move those electrons down here to this carbon to form an aldehyde. So it will form ethanol first, okay? And then the second step, if we put it under reflux, which I will talk to you guys about in a minute, if you allow the reaction to continue going, then the alcohol or the aldehyde will then actually form a carboxylic acid. So the end product would be the carboxylic acid. You can stop it in order to get an aldehyde, or you can keep it going to form the carboxylic acid. Okay, because you're again adding the oxidizing agent, so produces a source of oxygen to continue that oxidation into a carboxylic acid. And during this process, we go from orange to green. There you go. And you also have to have an acid in order to make this work, because you have to have a source of the hydrogen here in order to form this hydroxyl group of the carboxylic acid. Okay, so how would we do this practically in the lab? So distillation is often used to separate liquids with different boiling points. And because the aldehyde, which is the first step in the oxidation of alcohols, has a lower boiling point because they don't have hydrogen bonding as opposed to the alcohol and the carboxylic acids, that would be the final product. So you can actually separate the aldehyde through distillation, or again, stop the reaction. So basically, if you are performing an oxidation of this alcohol, right, and you want to get the aldehyde, you can then distill it in order to separate out the aldehyde. And then the carboxylic acid can also be separated from the reaction mixture by leaving the aldehyde in contact with the oxidizing agent for prolonged periods of time using something called reflux. So here, this step called reflux, I'm going to explain what that is. So reflux is where the vapors are collected and condensed to enable the volatile components of the reaction to remain there long enough to go to completion. So if you're distilling something, you're boiling it, right? Those aldehydes are going to be boiling out. But in a reflux apparatus, those vapors are condensed and then put back into the mixture to allow them to continue on to form the carboxylic acid. So it's really cool. If you don't want the carboxylic acid, you would just distill it and collect the aldehyde. But if you want the carboxylic acid, you'd have to put it under reflux and collect those vapors and put them back in the mixture, and then they could go on to form the carboxylic acid. Yeah. Okay, so that was with a primary alcohol. What if you have a secondary alcohol? Instead of forming the aldehyde and then the carboxylic acid, these are going to be oxidized to form ketones, similar to the oxidation of the primary alcohol. But because this is a secondary alcohol, this carbon with the hydroxyl group is attached to two other carbons, so it's secondary. It's not going to form the aldehyde, right? Because there is no this carbon is not bound to a hydrogen, it's bound to another carbon. So instead of that happening, it's just going to form a ketone. So it's going to form that double bond here to form propanone, because we're starting with propan 2-ol here, so it's going to be oxidized to form propanone. And you're going to, again, do the same thing. You are going to add the oxidizing agent and add heat. And again, it's acidified oxidizing agent, so you have to have an acid in there. And under reflux, and it can go into and form propanone. Notice that water is a byproduct of the reaction here, and that's because you have the removal of the hydrogen here from this carbon and the hydrogen from the hydroxyl group, and it combines with the oxygen from the oxidizing agent, so it can form water as a byproduct. Okay, what about tertiary alcohols? They do not oxidize readily under comparable conditions. So if you have something like 2-methylpropan 2-ol, where we have this carbon attached to 3 other carbons, it does not readily undergo oxidation because we can't form a double bond now, because we're not going to be able to remove this methyl group here under normal conditions because of its stability. So you're not going to see any change in color from the oxidizing agent if it's a tertiary alcohol. All right, so here is a summary of the oxidation of alcohols. So we have oxidation with potassium dichromate. So this is going to be causing the oxidation of primary alcohols and secondary alcohols, but not tertiary. So it's going to go from orange to green for both primary and secondary alcohols, but stay orange for tertiary. And remember, during a primary oxidation, it's going to form the aldehyde, and then under reflux, undergo more continual oxidation to form the carboxylic acid. Secondary alcohol is going to be oxidized into a ketone, and then a tertiary is not oxidized. Okay, and additionally, it can, instead of being oxidized, alcohols can also undergo something called esterification, which we also talked about last year. So this happens when one reactant contains a carboxylic acid group and the other contains a hydroxyl group. And together they can react to form an ester, aka esterification. So remember, carboxylic acid plus alcohol makes an ester and water. This is an equilibrium reaction. So just letting you guys know, that's why you can see the equilibrium arrows here. The name of the ester takes the name of the alkyl portion of the alcohol and then by the name of the acid salt. So, for example, we have ethanoic acid here because we have the 2 carbons, and then we have our carboxylic acid group and ethanol. Here, you can see that the hydroxyl group of the carboxylic acid and the hydrogen of the alcohol are going to combine to release water as a byproduct, so it's also a condensation reaction. And then it's going to form an ester bond. So then this bond here between this carbon and oxygen is then going to be bound here to this oxygen. So that is going to be our ester bond. And this is now going to be ethyl ethanoate. So the name of the ester, the ethyl part here, is from the alkyl portion of the alcohol. So if this was methanol, it would be methyl ethanoate instead of ethyl ethanoate. And so if we were going to write it here without drawing it, you can see we have ethanoic acid and ethanol here, and then you put the sulfuric acid above the reaction arrows because you need to have a acid catalyst to make this happen, and you make our ester and water as a byproduct. Normally water is the byproduct of this reaction, but it can be hydrogen chloride or ammonia can be the byproduct of an esterification reaction. So the conditions are going to be higher temperature and sulfuric acid catalyst. So esters usually have a sweet or fruity smell and are used in food flavorings and perfumes. Unlike the parent acid, the carboxylic acid and the alcohol, esters don't have that free hydroxyl group, so they can't form the hydrogen bonds, which makes them more volatile and less soluble in water, which is why they're oftentimes used in perfumes. Naturally occurring fats and oils are also esters. So like forming triglycerides have ester bonds in them. They contain 3 ester bonds actually because they react with an alcohol that has 3 hydroxyl groups and 3 carboxylic acids. So 3 carboxylic acids and 3 alcohols can make the triglyceride to form 3 ester bonds. Okay, so we're done with alkanes, alkenes, alcohols, and now we're moving on to halogenoalkanes. We're making our way to the end, guys. So halogenoalkanes are the same as an alkane. It's just one of the hydrogen is substituted with a halogen. So they are saturated because they only have single bonds, and then they have either a fluorine, chlorine, bromine, or iodine bonded to the carbon skeleton of the molecule. So due to the presence of this halogen, the polar halogen, they have a polar bond, unlike a nonpolar alkane. So because of the polarity of this, they're more likely to undergo substitution reactions. So this undergoes something called nucleophilic substitution, and I'll explain what that is in a second. Okay, so the halogen is going to be more electronegative than the carbon, so it has a stronger pull on the electrons, which gives that halogen a partial negative charge. So you can see here this is represented by the little delta negative here with this chlorine bonded to this carbon, and so the carbon will be partially positive. So because this carbon is partially positive, it's said to be electron deficient. So this is what defines the reactivity of the halogenoalkane. How electron deficient is that carbon? So nucleophiles are reactants that have a lot of electrons, and they're very attracted to electron deficient atoms. So nucleophile, phile means loving, right? Nucleo is, positive, the nucleus. I mean, even though this isn't attacking the nucleus, but nucleo means positive. So this really likes positive things. And because this carbon is now partially positive, nucleophiles are very attracted to it, which is why it can easily kick out that halogen and bond there instead. So nucleophiles have a lone pair of electrons on them because usually they're attracted to positive things, right? So they're going to have electrons and they're going to have a negative charge. So things like water with the lone pairs on the oxygen, hydroxides, ammonia with the lone pair on the nitrogen, and cyanide with its negative charge. Those negative charges are going to be attracted to that carbon, attack it, and kick out that halogen and take its place. So it's going to be substituting. So for example, we have chloromethane here. That chlorine is going to make that carbon electropositive. So if you put it with a base, something with a hydroxyl group, that hydroxyl group is then going to be attracted to the carbon and take the place of the halogen. So it will form methanol and then sodium chloride because the sodium will then pair up with the halogen that was kicked out. So if you have bromopropane and then add it to an alcohol group, again, that alcohol is just going to take the place of that bromine. So when we get to HL stuff, you're going to have to understand the mechanism of how this happens. But for now, just for SL, you just need to know the products of this reaction. Our last one, guys, we're almost there. We're going to talk about the reactions of benzene. Okay, so you remember, benzenes aren't like normal alkenes, right? Because that arene ring and the resonance is very stable. So instead of undergoing addition reactions, they're more likely to undergo substitution reactions, which we have talked about previously. So one or more hydrogen atoms is going to be replaced by whatever the incoming group is that's reacting with it. So substitution, it does occur on the delocalized electron ring, but the delocalization is preserved in these substitution reactions. And this is called electrophilic substitution. So last we had nucleophilic substitution, and now this is for the halogenoalkanes, and then now this is electrophilic substitution. So an electrophile is something that loves electrons. So this, instead of having more electrons in it, is going to have partially positive charges. So they're going to be attracted to the electron-rich benzene ring. So that is what is going to allow it to want to take the place of one of the hydrogens on the ring, is because these are attracted to these all this negative charge in this ring here. So example of this, benzene can react with NO2 plus here, and I'll show you how that happens. So NO2 plus is the electrophile, right, because it's partially positive. That can actually form from nitric acid. So if you combine benzene with nitric acid, that NO2 plus will form because nitric acid and sulfuric acid combined makes NO2 plus, and you don't need to know about how that happens, but it happens. And then that NO2 plus is attracted to that benzene ring, so it's going to kick out that hydrogen, and the NO2 is going to replace one of the hydrogens and then form water as a byproduct because of the nitric acid is HNO3, right? So the extra OH and the H that it kicks out combines to make water. And it can also do this with halogens. So normally chlorine isn't thought of as an electrophile, but if you separate the charges and form chloride, then the other chlorine will be electropositive, will be electron deficient, and then that benzene ring can attack that positive, right, electrophile in order to bond to it and kick out the hydrogen. So that would form a benzene with a chlorine attached to it and hydrogen chloride gas. And again, what's above the arrow are the conditions / catalysts needed for this reaction to occur. Okay, the last thing we're doing, guys, let's practice. So I want you to practice writing different equations for the reactions that I talked about, predicting products, explain what nucleophilic substitution is, and explain why benzene likes to undergo substitution rather than addition reactions. Okay, that is it. I managed to keep it under an hour. I'm proud of myself. I'll see you guys in class. Bye.